There we go. Math and Comp Sci McMaster. This should be a perfect workshop for you. T-shirt. McMaster and Engineering 1, Comp Eng, second year. Cool. iBio as well. That's awesome. Second year software engineering. You're probably taking 2D4 with me. That course is great. Yeah, very applicable to software engineering as well.
I guess we can introduce ourselves, or I'll introduce myself. I'm Trinity. I'm first year Eng at McMaster.
Hey, so I'm Omar, third year of software engineering and society at McMaster University.
I'm Young, and I'm also second year software at McMaster.
All right, we got 21 people in the call. We'll wait around 7:05 and then we'll get started. Let's do a quick introduction, then we can get into the content. All right, we got more people trickling in. We're at 24. We'll start around 7:05, 25. There we go. For those just joining in, be awesome if you could share your program, your year, and your university in the chat. Eng 1, awesome. Engineering physics, that's really cool. Software Eng 2, CS first year. Eng Phys, hi Manan. Software engineering at McMaster, I finished year 3. That's awesome. Probably on co-op, like I might guess. Hopefully you're enjoying that too. Thank you, Manan. All right, we're almost about to start. 7:04. We'll start in a minute. We've got around 30 people on the call. That's awesome.
All right, it's 7:05. Let's start presentation. So, hi, I'm Young, and this is machine learning with Sklearn in 1 hour.
Yes, I can introduce myself again. I'm Trinity, and I'll also be talking briefly today.
Hi, I'm Omar, third year software engineering at McMaster. Yeah, happy to meet y'all. Hopefully you learned something great today.
You can go full screen if that is okay. Okay, so I'm just gonna first start off by defining artificial intelligence as a whole. So a lot of people use artificial intelligence, machine learning, and deep learning all interchangeably, but they're actually separate things. So artificial intelligence includes machine learning and deep learning, and it basically means a machine acts like it makes human-like decisions, but that doesn't necessarily mean that it's actually learning anything. Machine learning is when the machine learns, and it takes data that we can input, and then it can make predictions based off of this data. But we still need to guide the machine a little bit and break the problem into different pieces and help the computer process the information correctly. With deep learning, the machine can use neural networks to process the data all by itself. So we have a couple of examples. So artificial intelligence is like chatbot. It seems like it's like a human, but machine learning is when we have like decision trees and logistic regression, which we're going to learn today. So here's kind of like a pipeline, so like the machine learning process, which we're going to be doing today. So first, machines need data to learn from. So we're going to need to gather a good data set and process it in a way that our computer can actually understand. So like we can't just give a computer a whole bunch of images and then it's going to understand what's in those images. We need to process it first. And then in machine learning, we train a model off of this data. So models are what recognize the patterns in our data. So not all models are going to pick up the same patterns or be the same. So we need to choose one that works for our project. And then we train this model by taking all the data so that it can try and make predictions. And then that is when we can evaluate how successful this prediction is. And then we can tune our machine based off this evaluation. And we're basically going to keep going through these steps again and again. So like, let's just say we're not satisfied the first time. It's probably going to happen. Our machine's not going to be perfect. The first time we'll need to gather more data, then process that data, maybe train it again, or we'll have to train it again. And we'll just keep going through that process again and again to improve our machine. So Sklearn is a machine learning library. We can use Python, and it's supposed to be an introduction to machine learning. It was created by Google, I think, as a summer code project, and it just provides tools or tools for steps of the pipeline. So, for example, we'll use it to test our model's performance today. So you'll be able to see today just how Sklearn helps you with machine learning.
So let's get to the code portion. First off, you guys should all have this Colab notebook. If someone could just send that in the chat real quick. Once you're on this notebook, you want to click File, and let's first create a copy. So go to File, then click Save a Copy in Drive. Take a minute, and then it'll create a copy of this template, which you can use to follow along if you'd like. Close our old template. Now we have our copy. So I should mention that I won't be stopping for like questions. So if you have any questions, just shoot them in the chat and someone can just yell out. Let's start with our imports. We got to import pandas and NumPy for this first step. Pandas is a Python library for data manipulation and analysis, and NumPy is a Python library for scientific computation. More specifically, it helps with dealing with matrices. And in this first step, gathering data, this will typically be done through.
Sorry, Young. Somebody wants us to repeat the first step real quick.
Yeah, okay. So go to the Colab notebook, click File, and then click Save a Copy in Drive.
Also, the Colab link is in the Zoom chat. You should take a look at that. That's where you'll find it.
Okay, so typically this gather data step would be done through API calls or web scraping, but for now we're just going to use a pre-built data set. Let's load our data set in. Let's load it in as a pandas data frame by calling df_raw for our raw data and saying this equals pd.read_csv, and let's read from the URL. So now that we have our data frame loaded in, let's take a look at it by using df_raw.head to look at the first 10 elements. So we could also use df_tail to look at the bottom two, but let's keep it ahead for now. So looking at our data frame, we can see that we have a lot of data, right? We have different variables, different features that could use. Okay, before that, let's introduce our data set. So our data set gives multiple different variables about patients, and our goal is to try to predict whether they pass away or not. So as you can see, we got like the patient gender, height, ethnicity, age, all this stuff that could potentially contribute to if a patient passes away or not. And further examining our data set, we can see that it's kind of messy. Like we have this unnamed 0 column, we have 2 gender columns, we have missing values. So if we just fed this into our model outright, 1, it wouldn't work. But 2, even if it did, it'd give us some like results that, unwanted results, because something like patient ID wouldn't contribute to if a patient dies or not, right? So let's first, so to deal with that, we have to clean up our data. So before that, let's take a look at our columns and say df_raw.columns, right? So here again, you can see we have this unnamed 0, hospital death. Here's our output, patient ID, 2 genders. So let's get rid of those. To get rid of those, we'll make a list called remove, and then we'll remove the columns we don't want. So we want to get rid of this one. We also want to get rid of patient ID. Let's also get rid of this second gender column. Finally, let's get rid of ethnicity because, I don't see color. And also because you can see ethnicity is a string while everything else is numbers, numerical. So if we put this into our data, into our model, it wouldn't necessarily work. There are workarounds, but for the context of this workshop, let's just get rid of that outright. And to get rid of it, we'll say df_raw.drop, and then let's drop the columns in our remove list. And we'll say axis equals 1 to indicate we want to drop the columns. It's typically good practice to create a new data frame and keep your original data frame data set untouched if you ever need a reference back to it. So now that we have it removed, let's take a look at our newish data frame. So df.head again, you don't have to specify anything. The default is 5. So you can see, okay, we got rid of the second gender, we got rid of patient ID. So it's looking better, but we still have 2 more issues. We see this gender column here. We have F and M, everything else is numerical. Let's deal with that. And also we have missing values. Let's first deal with replacing F and M with 1 and 0, something that our machine can understand better. Let's do this by saying, let's do this by saying df gender, right? To specify you want to do with the gender column, dot replace F and M with 0 and 1, right? And we'll specify in place equals true to modify our data frame. All right, now let's check if there are any infinite or missing values. So here we can see we have missing values and don't have any infinites. Let's first deal with the missing values by saying df.fill_na with df.mean and in place equals true. So what we're doing here is replacing all these missing values with the mean of the data set. So these missing values will all get replaced by the mean in every single column. Another way to deal with this is to say df.dropNA in place is true, right? This will just drop the missing it'll just drop any rows with missing values. This is another approach to dealing with missing values, but for the sake of this workshop, let's just replace it with the mean. Now we don't have any infinite values in our data set, but you'll notice that machine learning does a lot of copy and paste. So we can just show one way to deal with missing values for your future reference. So let's say df dot replace, and let's replace all np dot infinite. So any infinite values and any negative infinity values, let's replace those with np.nan. So let's just replace any infinites with missing values and then say in place equals true. And then once we replace all the infinities and negative infinities with blanks, let's just get rid of all those blanks. With the same command, drop NA. In place equals true. All right, now let's take a look at our new data frame. Let's say df.head again. So here we
Young
can
Tushar
see,
has a question that
yeah.
what is the reasoning behind choosing the mean value to fill out the missing values versus just like dropping the rows entirely?
So in this case, it's just so these missing values don't have that much of an impact. So let's say we replace all missing values with 0, that would like show significantly more correlation. Like for example, let's say this person number 4 died, right? They had all of these missing values. If they had weight 0, BMI 0, then the machine will learn values that aren't like, it will learn from information that isn't necessarily corollary, so it doesn't really matter, right? Another approach is to just drop these rows outright. And I encourage some people to try this out. Maybe you'll get some better results than me. They're just two different ways of dealing with missing values. Yeah, thanks for the question. But yeah, now we have our data frame that's looking a lot nicer. But one more step in this section is we have to separate our values into y and x. So you can think of y as the output, right? If you think of an equation of a line, your y is your output, and your x is all these different variables. So for example, x1 could be age, x2 could be weight, right? And what our model wants to do is find out M1 and M2. So how much weight should we put on age and weight? So for example, maybe age, we could give it a high weights by saying, because like generally if you're more elderly, you have a higher chance of passing away rather than if you're young. When weights, maybe weight by itself isn't too good of a indicator because weight fluctuates a lot with height. It could be like fat, muscle, right? So our model will try to find these M1 and M2s given our X1 and X2s and try to predict our Y, which is our output, being hospital death. And for all my homies that took linear algebra, you can probably notice that this is just the matrix multiplication. And spoiler alert, behind the hood, a lot of machine learning, deep learning, all that has to do a lot with matrices. So to create our X and Y, we'll say X equals df dot drop, right? Let's remove our output, right? We don't want to be considering our output as a variable for like, if we don't want like the answer on the test to be in the X values, because then all the M's would be 0 and you would just give full weight to hospital death, right? So let's drop that from our X and say in place equals false is false. So the default is false, but I'm doing this to reiterate that when we say true, we're changing the data frame outright, and we say false, we're just making a change and saving, and we can use it to save into another variable. and our Y is hospital death column. Hospital death, okay. Let's spell hospital death now. Okay, so now I'll give it to Omar to explain the next section.
All right, splitting and scaling, the math part. All right, so something that is very crucial to machine learning and data science in general and data processing is something called data normalization. And one of the most popular ways to do this is min-max normalization. So let's see what data normalization is and why you would want to do it. So generally, data set attributes are on very different like scales, right? Apologize for the typo there. On very different attributes should be on very different scales. So if you consider a data set that gives you house prices, it might have columns like rooms, it might have the price, it might have the age. But if, for the sake of argument, if the value of rooms is the one that dictates the house price the more, like it has a higher weight to the answer, because of the fact that age is from 1 to 70, when you train your model, you might actually get a bias towards age because it has to have a higher weight because the range is higher in your model. So to deal with this, what we do is we try to normalize the scale so everything is on the same scale. And there are many methods of normalizing your data. One of them is min-max normalization. There's log scaling, and then there's z-score, and there's many different others. You could pick and choose depending on your problem and whatever works best for you. So min-max normalization is the simplest form of normalization to understand. Basically, all we do is we scale all the values based on the minimum and maximum values for each attribute. So if rooms goes from 1 to 5, we'll pick 5, and then we'll divide everything by 5. That has the effect of basically making sure that everything is between 0 and 1. So 5 over 5 is 1, 4 over 5 is 0.8, it goes on to 1 over 5, which is 0.2. And then you could also do the same for price. So if minimum price is 200,000 and your maximum price is 1 million, you could do 1 million over 1 million, 500,000 over 1 million, 200,000 over 1 million. So we're still on that scale 0 to 1, and you could do the same thing with age. And this has the effect of basically normalizing all of your data so everything is on the same scale, and there's a better chance that it won't introduce any unwanted bias or unwanted weights in your machine learning model. All right. So another important thing is data set splitting. So if I give you, let's run with the house prices data set example. So let's say I give you 1,000,000 points, 1,000,000 like entries for your data set. So what you want to do is you want to split it into two sets. One of them is for training your model, and the other is for checking whether your model actually predicts something correctly on something it hasn't seen before. So the training set is basically whatever you use to train your model, and validation is what you use to check. If I use something from a validation set into use something in my validation input, we'll plug that into our model and see what it outputs. And because we already know that the points in the validation set are correct, we can actually get an error value and see how well our model is performing. So there's a rule of thumb. It's about 80 to 20%. So 80% you want to use to train your model, because whenever you have more data to train your model, it is obviously going to perform much better. And this also depends on the scale, how many data points you have. If you have like 1,000 data points, it's probably fine to go 80-20. But if you have like 10 million points, it might be better to go 99 and 1, right? Because you don't need that many data points to verify your model. But generally, you want to go with an 80-20 split or 70-30, or that also scales depending on the size of your data set.
So let's go to code and let's code up just that. So let's start off by splitting our data into the 80-20 split, like Omar said, by doing x_train, x_test, y underscore train and y underscore test. This is train test split. We give it our x column and our y, and give it a test size of 0.2. So now let's just double check the size of our training and testing data. Here we can see, right, our train set's 80, our test set is 20. So now you can see like the power of sklearn. If all that math stuff was a little confusing, don't worry about it, because sklearn makes it really easy and really simple. Because to normalize, all we have to do is create a scalar object and create an instance of sklearn's min-max scalar. And then to scale our data, we just do x underscore train equals scalar. So we use our scalar object dot fit underscore transform on our data set, on our x data. So here we'll do the same for our testing data. And in this case, we'll just want to transform it rather than fitting to it. This prevents what's called data leakage. And that's when your model learns from data it's not supposed to. So we did fit here, then we'd be finding out data from our X test, which should be reserved for just testing how well it does. So let's take another look at our X variables, our X matrices now. So here, as you can see, it's like, this doesn't really mean much, but all our values are normalized. And while it might not mean much for us, it's a lot easier for our model to see, to consume and understand. So now let's talk about model selection. So speaking of our model, there are many different types of ML models. You have decision trees, logistic regression like we're doing today, or neural networks you must have heard of. And we're choosing logistic regression because it excels with binary classification and it's relatively easy to understand. In this step, a couple of important factors to choose your model are the type of problem. So be it classification or regression, or it could be like recommendation, like YouTube's algorithm, right? The type of data you have, is it images, text, numerical, audio, different networks and different models excel with different types of data, and how much data you have. For example, we're using logistic regression, but if you had a whole lot of data, maybe you could use a neural network and get even better results. And then let's give it to Omar to explain logistic regression a bit more.
All right, so we got more math. I wonder why. So the logistic function is the equation you see on the right on the slide there. Now, if it looks terrifying, you do not need to be terrified, because usually when you're working with them in the field of machine learning, you don't exactly need to know all of these specifics. So the logistic function is just a sigmoid function, and you can use it for classification problems and regression problems. So classification problems are things like, if I give you a data set and I tell you like this is red and this is green, or this picture is a cat and this picture is a dog, you might be able to use logistic regression to classify that. Basically, what would happen is that the logistic function outputs a probability, and that probability you can actually you could define that if it says that there's an 80% probability that it's a dog, you might say that, yeah, it's probably a dog. And the converse of that is, if it's saying that it has an 80% probability of being a dog, your picture, that means your cat, it has a 20% chance of being a cat. And then you can adjust that probability value. It could be 80, it could be 85, it could be 50, depends on what your data set yields. And the thing is, this is best suited for nonlinear data sets. So the other thing that we usually talk about when introducing machine learning is linear regression. And that is basically drawing a line through curves. It's called the line of best fit. You might have seen that before in high school. That is also machine learning technically. The problem with that is not most problems in the world can't be classified using a straight line. So the non-linearity of the logistic function is very helpful when dealing with such issues. All right, next one. All right, more math. So how do we train our models? It might seem like magic. How does the machine learn? So one of the ways it learns is using a gradient descent algorithm. And this is basically an optimization function. And you can see that in the top right corner of the slide there, that is the function we're talking about. And if it looks scary as all hell, do not worry about it. If you haven't taken the calculus courses from first year, you probably don't know what that means yet. That's perfectly fine. We don't need to know the specifics about the math at this moment. So basically, to talk about this function, we have to introduce what the gradient is first. It is basically the derivative of a function. So when you have a univariate function, which is just f at x, the derivative is just the slope of the line tangent to the function, right? At that specific point. And if you think about it, in a three-dimensional function, which is a multivariate function, you'll get a vector instead of just a tangent line, if that makes sense. And you can generalize it to 4 dimensions and however many dimensions. So the only problem, there are some limitations to gradient descent. The function that you're working with has to be convex and non-convex because of the way it works. So if you see in the top part of the slide there, if you show a convex and non-convex function, basically if I'm able to draw a line from one point to the other, it will not cross the function whatsoever, which means it's convex. It's kind of like a U bowl shape. Non-convex, as you can see in the second figure there, when I draw a line from there to 1.5 around there, it does cross the function. That's non-convex. And the reason for this is that the way this works is that it will basically take the derivative, it will look at your function, take the derivative, and it will go in the opposite direction of that. Right? Because we'll talk about why it goes in the opposite direction, but you can see it working on the top bottom right image there. That's basically gradient descent working. It works in discrete steps, so it will try once and it will take a second step, a third step, fourth, fifth. Usually they go on for a very long time, but that is gradient descent working on the bottom right image there. Take a look. Probably look at it for a couple seconds. So it starts off at a point. Just wait for it to restart. It starts at a point and then it moves to the next point. It tries to minimize the function because it is an optimization function. If you remember from high school, it's just either finding the maximum or the minimum of a function. And that's what it's trying to do there. Sometimes it works, sometimes it doesn't. And in that picture there, it's not working because you see it goes down. It tries to go towards the minimum, and then it starts bouncing back up. So that is something that does not converge. It is not able to minimize that function, and it'll basically get stuck in that saddle shape there. So that's why we want our function to be convex. That's why it works best for convex functions. And of course, it has to be differentiable because you are computing the derivative. Also, could we go back for a second? Just forgot to mention learning rate. So another thing we forgot to mention is learning rate. So learning rate is basically defines how big of a step gradient descent will take for its next step. It could either be a very small step, which means you're more likely to reach an optimal solution, but it will take much longer. So in that animation on the bottom right there again, it is taking pretty big steps, which is why it misses the minimum there, which is around x equals 1.5, and it just bounces back up, right? But if we made those steps much smaller, it would follow the function all the way down to the minimum, and it would say, hey, I'm at a minimum now. And hopefully that's the right answer. But if you increase that learning rate, your model will converge faster, it will train faster, but it could also mean that it has reached an unoptimal solution. So you also have to play around with that. It's just one of the things you tune when you're training your model. So more math. So we mentioned before that we want to get an error between our validation set, the one that we use to validate our model, see how correct it is, and the expected outputs. So the way we do that is by defining what is called a cost function, or it's also called a loss function. It's a function that defines the error between the predictions and the actual values of the training set, or your whatever you're predicting. So for logistic regression, the most popular function used is the log loss function. It's also called cross entropy. Fancy names, don't need to worry about what it means. Sounds scary. So the log loss function is in the top right of the slide there. Because we are going to try to classify whether our patients are going to live or whether they're going to pass away. We have two classifications if yp is equal to 1, and we also have yp equals to 0. We'll define that in the code, and that is the loss function. So you don't need to worry about calculating this yourself. Sklearn and other machine learning libraries will do this for you. And as we mentioned before, gradient descent is an optimization algorithm, right? So we basically want to minimize this cost function, and that's what it's trying to do. It is looking at the cost function, it is computing the derivative, and it is trying to take a step towards hopefully the direction that has the minimum value. So that's why it goes against the derivative. And in the case of higher dimensional functions, it will point towards the area in which the function increases the most. So that's why you want to go in the opposite of the gradient or your derivative. And you can see in the bottom right there, that's basically what the cost function is. That's a very simple explanation, like example of it. You have a line of best fit, and those green points are the ones that, what are the actual values that you're supposed to expect, and the red lines between the points are basically the error values. So whenever you input one of those green, whenever you input something on the X, it should have come up at the green box, but it didn't. And the difference, the vertical difference between the line and the actual expected value is your error value. And if you've used decimals before, you've seen those are called residuals. That's also an example of machine learning. So we've talked a lot about the math. So any questions about that? And feel free to ask them in the chat.
While waiting for questions, let's get back to the code. Again, if you didn't understand that, don't worry, it's pretty complicated. Probably the most difficult part of machine learning is the math. But here you can see the power of sklearn again by like you'll see how simple it is to actually implement all that. So to create our logistic regression, all we have to do is create a model, logreg, and just create an instance of logistic regression from sklearn. And boom, we have a model just like that. To train our model is just as easy. All we have to do is logreg our logistic regression and call .fit with our x train and y train values. Right? And boom, all that about gradient descent, cost function, whatever, like sklearn makes that so simple. If you just .fit, boom, it trains our model for us. Now let's see how well our model does on the testing data by calling logreg.score and pass in x_test and y_test. And wow, look at that, 92%. That's pretty good, right? But to put that 92% into perspective, let's take a look at our null accuracy. So basically, if our model just guessed that no one ever died, and if the model guessed no one ever died, let's check out what that score would be. And 91. So our model is only 1% better than like a useless model that just guesses that no one dies. So to see why, let's look at the balance of our data set. So we can see that the amount of people that have passed away versus the amount of people that have survived it's significantly less, right? So this results in an unbalanced data set. To deal with this, we're going to have to choose a better evaluation metric. Now let's get on to eval metrics. Eval metrics are used to measure the quality of your model. And as you saw, selecting the incorrect evaluation metric can skew your perception of A, how you think your model is doing, and B, most importantly, how your model thinks it's doing. And if your model thinks it's doing great, but it's actually doing pretty poorly, it will optimize incorrectly and, as you saw, like not give the best results. For a quick example, let's take a look at an example data set. If there were 10 total patients and 1 death, if our model just simply predicts that no one ever passes away, if we use accuracy as an eval metric, which can just be thought of as the total number of correct predictions versus total predictions made, you can see our model gets 90%, right? So it predicts 9 correct cases where the patient survived and 0 correct cases where the patient passes away. So we get a score of 90%. However, if we used another evaluation metric called balanced accuracy, which takes the rate of correct classifications, we can see that the model got 100% of the classifications where a patient survived, but 0% on classifications where our patient passed away, resulting in only a 50% balanced accuracy. So I hope this illustrates how selecting the correct evaluation metric can really skew how well the model seems to be doing. So to implement that in code, let's create a variable ypred. This is the predictions of our model, and let's use our model logreg.predict on our X testing data. Now let's look at what Sklearn calls a classification report. So this might be overwhelming, but let's just focus on these 2 columns right here. So F1 score, and like we suspected, our model is doing really well at predicting if a patient survives or not at 96% F1, but it's doing pretty poor when predicting if someone does pass away at 32%. And while this gives us a really high accuracy, we take a look at balanced accuracy by saying balanced accuracy, give it our actual labels. Let's compare the actual labels using y-test and our predicted labels using ypred. And let's take a look at this. So here we can see our model is only getting a 60% balanced accuracy. So you can see that our model isn't doing that great. Right? Let's just save this value for now. Default. Let's create a default score value just to save this value for later. And we can see our model is pretty bad right now, right? How do we solve this? Well, one way to solve it is through parameter tuning, which is the next step. So parameter tuning, you can think of parameter tuning, specifically hyperparameter tuning, you can think of as the finer details of the model, right? If the model and the data is the meat and potatoes, the hyperparameter is the sauce. It can really make or break a meal, and it can really make or break performance of our model. Examples of hyperparameters could be the number of gradient descent iterations you run, regularization, which is how much weights you put on each iteration of gradient descent, or learning rate, like Omar mentioned. When we first trained our model, we initially assumed a lot of values, basically just using the defaults, but now we can change those values and see how doing that can improve our model performance. We'll do this by doing a parameter search. 2 typical parameter searches are grid search and randomized search. What's the difference? So grid search tests all the possible combinations of parameters you give it, while a randomized search just tests a random combination of them. And to answer who cares, let's go to the code and you'll see why. So we're going to be using a randomizer for the sake of time. And first off, we have to create a new logistic regression model because our previous model has already seen all of our data. And let's create a param dictionary of hyperparameters. So hyperparameters, let's go to this link here. We can see this is the Sklearn docs, and we can take a look at all the different hyperparameters. You can see it's a bit overwhelming, but I encourage anyone afterwards, if they're interested, to go to this website, take a look at the different type of hyperparameters you consume, and see if changing any one of these can improve your model performance. But right now, you can just follow along if you'd like. We're going to be changing 3 different parameters: the C value, which let's give it a range of 0.5. And 2, the C value is the inverse of, it's the inverse of regularization. You can think of it as the higher value, the less weights you give to each iteration of gradient descent. And we have our class weights, which is, you can think of this as how much focus we want to put on each class. We can see that there are way more patients that survived than passed away. So let's try to give more focus and more attention to predicting if our patient passed away. Let's give more focus and more attention to any predictions our model makes on if a patient passed away. And max iter is just the number of iterations of gradient descent, so how long our model will run for. Let's run this. So here we have our parameter dictionary. To use randomized search, we have to create a randomized search object from Sklearn. We'll give it our log-reg model as the estimator, parameter distribution, our parameter dictionary. Scoring, we'll use balance accuracy. And iterations will do 1. So here you can see the power of randomized search. So let's take a look at how long it takes for one. Let me see. Not balance. I spelled balance accuracy wrong. Yes, I did. Okay, so it takes 3 seconds for each iteration. What does this tell us? So this lets us know that if we wanted to run it for, let's say, 10 minutes, we just scale this up. So, for example, if you wanted to do a parameter search and you know you're going to go for lunch for 30 minutes, you can do 1 iteration to see how long 1 takes, and then run another parameter search to make sure that when you come back from lunch, you'll be finished computing. So if it takes 3 seconds to do our parameter search, for the sake of time, let's only take 10 seconds, and 3 times. Let's say, sorry, we'll take 10 seconds, and we'll set max iter as we'll set as 4, right? So now we can estimate that it'll take roughly 10 seconds, and obviously after we find our parameters, let's fit it on our training data. Okay. All right, should be find the training data. Yeah, so you can see that now it's running for 4 iterations. If we did a grid search, it could take significantly longer because it would test out every single combination. So we see we have 5 potential class weights, we have 4 potential C values and 4 potential iterations. Like, do some quick math. That's it's about like 80 iterations of randomized search and of grid search, which could potentially take a lot longer. While randomized search, we get a lot more control. Let's take a look at the best parameters it found by running rand.bestparams. So here we can see the different params it found. So for anyone following along, you probably found different values, and that's simply because we only ran our randomized search like a couple times. So maybe the values it tested for me are different than yours. You can put these values into our new logistic regression model. So you can see max iter 500, class weight of 1, 4, and a C value of 2. So there's our new model, and we have to fit it again on our training data. And fit it on our training data. We'll predict it, which is just as easy by just saying log reg dot predict it on our testing data. So x underscore test, we'll save it as y underscore prediction. And let's calculate our new balanced accuracy by saying balanced accuracy score, giving it our true labels with y test and our predicted labels with y underscore pred. And let's compare our new score with our old score. And look at that, just by changing a couple hyperparameters, we improved our model performance by 9 points, which is pretty significant, right? So now you can predict if someone will die. Let's go back to the slides. And yeah, that pretty much concludes our presentation, but leave you with this May and a couple of resources. So I know most of you probably won't check this out, but these are the docs. This is a textbook for machine learning. And maybe some of you might check this out. Like, these are some YouTube channels that make really entertaining and informative content on machine learning and deep learning. Check them out. I would highly recommend. And one thing that I've been hiding from you, some of you might have noticed, but these images made here were actually machine made. Like, an AI created these images. And if there's one thing you take away from this, I hope you learned something, first of all, but if there's one thing you take away, machine learning, AI, deep learning, like, this stuff is really cool. So I really highly recommend going to these links and testing out Stable Diffusion and Dolly Mini and see what cool artwork you can create just by typing in a couple sentences. So also remember to join the Discord and fill the feedback form out. Join the Discord for updates on future events and fill out the feedback form. I know no one ever does that, but please. Let me send the links to these, because these are pretty cool. Just check them out. If you create anything really cool, send it to the Discord. Yeah, don't worry. It's going to be all recorded. And join the Discord to stay up to date on the recording. So yeah, hope you enjoyed.
Of course, I'm muted. Thank you for reminding me. Yeah, so Kylan, could you post a link to Discord in the chat?
Yep, looks like somebody just sent the Discord link. It's right there. I can send it again.
All right, thank you for attending. We'll stop the recording now.